Hello, everyone, and thank you to the organizers for the opportunity to speak here. I'm going to talk about the role of leptonic CP violating phases in charged lepton flavor violating observables, which is a recent work we did with my collaborators Asma Abada and Anna Texera. The main motivation is that since the discovery of neutrino oscillations, which are the first laboratory evidence for new physics, we know that at least neutral lepton flavor is violated and that neutrinos are massive. Massive neutrinos, on the other hand, also open the door to charged lepton flavor violation and also to new sources of CP violation. If we minimally extend the standard model to accommodate massive Dirac neutrinos, which acquire their masses via the Higgs mechanism, we can accommodate a neutrino oscillation data, which is shown on the right here. But these types of models are very hard to test because, for instance, charged lepton flavor violation remains completely unobservable. And we also have a naturalness problem because the Yukawa couplings to the neutrinos need to be vanishingly small. Other possibilities for model building often feature some of the various seesaw mechanisms, which mostly feature heavy neutral leptons. And heavy neutral leptons are, for instance, or can be, for instance, in those models, massive Majorana neutrinos, which then in turn lead to lepton number violation and charged lepton flavor violation. In lepton number violation, or lepton number violating observables, there's also a crucial dependence on the CP violating phases. As you can see, for instance, in this plot here, where I have the effective mass of neutrinos double beta decay versus the lightest mass of the active neutrinos. And interference of CP violating phases leads to this famous neck in this plot, where the interference leads to a strong suppression of the effective mass. From this vast model landscape, which do explain neutrino mass generation, most of them feature at least two heavy neutral leptons, either at high or at low scales. And from a phenomenological point of view, TV scale heavy neutral leptons are very appealing because they offer a rich cLFV phenomenology. So they're great to test at experiments, and they're potentially within collider reach. To stay a bit more model independent, we take an effective 3+2 model, which is a simplified approach to in order to analyze the effects of CP violating phases on charged lepton flavor violating observables. Precisely in this 3+2 model, we want to ignore the origin of neutrino mass generation. We just assume that in addition to the three light neutrino states, we have two heavy Majorana neutrinos, which mix with the light spectrum. The mixing is then parameterized via 10 rotations. So we have 10 mixing angles, and we also have 6 Dirac phases and 4 Majorana phases. If we assume that the mixing angles are small, we can approximately parameterize the heavy light mixing with this rectangular matrix. And the 3x3 standard model-like block of the PMNS matrix is no longer unitary. And due to this, the leptonic W and Z vertices are modified. If we now take the sterile masses at the TV scale, we expect sizable cLFV rates at the one loop level. So this is a great opportunity to analyze the effects of CP violation in those observables. As a simple example, I've chosen here the decay mu to gamma, which is mediated at the one loop level by the sterile neutrinos and 4 and 10 5. And the decay rate can be written proportional to the absolute square of some cLFV form factor, which is in this case a photon dipole form factor. And it has the very simple expression, which is given here. So it's a sum of the mixing elements at the lepton flavor violating vertices here and here, times some loop function, which is basically a polynomial times a logarithm and depends on the internal masses. If we now assume that M4 and M5, so the masses of the sterile states, are roughly equal, and also the mixing angles theta alpha 4 and theta alpha 5 are approximately equal and small, we can explicitly insert those mixing elements here into the form factor expression and simplify in such a way that you can see the explicit dependence on the Dirac phases. You can also observe that if those phases add up to pi, we have a full cancellation of the rate within those simplifying assumptions. Other form factors, such as Z-penguins and boxes, are a bit too complicated to show here, but I want to stress that those also do depend on the Majorana phases. We can have a look at this numerically. Here I've chosen the observables mu2 gamma, mu2 and Z2 mu. And we again take the same assumptions. I take the plot here for 1, 5, and 10 TeV of the sterile masses, which is shown by the solid, dashed, and dotted lines respectively. And I assume that all phases are vanishing except for delta 1,4. Now, if we vary delta 1,4, we see that there's a strong cancellation happening once delta 1,4 reaches the value of pi. And we could do the same for the other Dirac phases relevant in this decay. We can do the same exercise with Majorana phases. Here, I only assume that 5,4 is non-vanishing. And as analytically expected, you can see that the decay rate of mu2 gamma is independent of the Majorana phases. But in mu2 and Z2 mu, which also depends on Z penguins, and mu2 also depends on box diagrams, you can see the dependence of the Majorana phase, and the variational behavior is amplified for larger masses M4 and M5. We can also have a look at the joint behavior if both Dirac and Majorana phases are present. Here I've chosen to fix delta 1,4 to the value of pi, so that all dipole-like contributions are cancelled. And then we can vary 5,4, and as expected, we again see the very strong cancellation if all phases are 0 except for delta 1,4 is pi. And then we start varying 5,4, and we see a very strong dependence on this Majorana phase of all of the decay rates. A bit more interesting is the observable neutrinoless mu-E conversion in nuclei or muonic atoms. And this process depends on all topologies and phases, meaning that there can also be significant interference between different contributions in this process. If we now vary 2 phases at a time, you can see in this contour plot here on the x-axis, we vary delta 1,4, on the y-axis 5,4, and the color code is the rate. And you can see here that here's again the strong cancellation happening at around delta 1,4 is equal to pi, but now we also have a strong cancellation if 5,4 reaches certain values. And with the contour lines here, you see that the cancellation points are shifted around depending on the other phase. A bit unexpected is that the process mu-E conversion also depends on the tau neutrino mixing angle. This is due to the fact that in the Z vertex, we have a sum over all neutrino flavors. And this contribution can be very strong depending on the tau mixing angles, meaning theta 3,4 and theta 3,5. This interference between different contributions to the process can also be constructive, can lead to large enhancements, like the white patches here, here, and here. They exceed a rate of 10 to the minus 13. All I've shown you so far is in a somewhat idealized situation. We have chosen our assumptions to make the effects of the phases best visible. On heavy neutral leptons, there are several experimental constraints that need to be respected. And now we want to do a parameter space scan. So some of the constraints are, for instance, from lepton flavor universality, such as W decays and Z decays, ratios of leptonic meson decays, and many more. From lepton number violation, we have neutrinoless double beta decay. From we want to stay perturbative, so we have to respect the bound of perturbative unitarity. And there are also electroweak precision observables, which are significantly altered in the presence of heavy neutral leptons. Most importantly, the invisible Z decay width. We now want to do a parameter space scan, and all those constraints are independent of the CPV phases, except for neutrino's double beta decay. We do the scan with relaxed assumptions. We now only assume that theta alpha 4 and theta alpha 5 have a similar magnitude, meaning we add some Gaussian noise around the values, and we still assume that the masses are equal to each other. And on top of all points that pass our constraints here, and also the cLFV constraints for vanishing phases, we vary the phases delta 1, 4, 2, 4, 3, 4, and also the Majorana phase 5, 4 for each point first randomly, and then also on a grid, including special values such as pi half and pi and all possible combinations of that. One thing we can then study are correlations between observables. Here I've chosen as an example the effective coupling of muonium-antimuonium oscillations on the y-axis, mu to gamma on the x-axis. Muonium-antimuonium oscillation is a doubly flavor violating process, and it only depends on box diagrams. And both mu to gamma and this effective coupling only depend on those 4 mixing angles. So we expect a very strong correlation. And indeed, as you can see here in the blue line, we have this kind of correlation. There are, of course, a few points deviating from this. This is due to contributions in mu to gamma canceling each other when, for instance, theta 1,4 and theta 1,5 are the same in magnitude but have opposite sign. But most of the points are indeed on this blue line, and we see a strong correlation. Once we switch on the phases, now the orange points are for random phases, we see that this correlation is lost, and it gets broken by the presence of CPV phases. This is even stronger visible if we include the points from our grid scan. Another example I want to show you is the correlation of the two observables mu-e conversion and mu to 3e. Both of them are dominated by Z-penguin diagrams. So naturally, we would expect a very strong correlation. And indeed, here's again a blue line appearing with some points deviating because of diagram interferences. But one thing I want to show you here is we have here the current experimental bounds in dotted lines and the future sensitivities of the comet and mu to e experiment and of the mu to 3e experiment. So if we just imagine that in the future we observe a signal at the mu to 3e experiment for the mu to 3e decay, let's say of order 10 to the minus 15, then if we assume CP conservation, which is done in many simplified analysis of heavy neutral leptons, then we would expect also a sizable rate in mu-e conversion. But once we switch on the phases, we see that this doesn't need to be the case. So what I want to say is that if we observe a signal in mu to 3e, but not at comet for mu-e conversion, this doesn't mean we should disfavor heavy neutral lepton models. In a more generalized setup, we let theta alpha 4 and theta alpha 5, all 6 angles, we let them vary independently of each other. And we randomly varied all of the phases. Of course, we apply all of the constraints. And then again, we add again random phases on top of the blue points. But additionally, we also vary the mass splitting within the width of the states, which can reach up to 200 GeV. And here you can see the same thing I mentioned earlier, just without simplifying assumptions. Here you see the branching ratio of mu to gamma and the conversion rate for mu-e conversion. And again, we can have the situation that MEC2 will observe mu to gamma without comet and mu to e seeing anything, but also the other way around. And this means that effects of CP violating phases are always very significant. This brings me to my summary and conclusion. As you have seen, the presence of CPV, Majorana, and Dirac phases can strongly suppress or strongly enhance the rates of cLFV observables with a significant impact on the interpretation of future data. Here in this table, I've chosen a few benchmark points. The first of which, where mu2 3e and mu-e conversion is within future sensitivity of the mu3e and COMET experiments, and tau2 mu and z2 mu tau are not within future sensitivity of FCC-EE projections. Now we can tune the phases in such a way that all of those observables will lie within future sensitivity, and this part of the parameter space can be probed by those experiments. We can also have the situation that our model gives us a prediction where the mu-e flavor violating sector is vanishingly small and cannot be probed. But once we switch on the phases, we can enhance the rates sufficiently that all of the observables lie within future sensitivity, or all our predictions lie within future sensitivity. For various reasons, our model might predict rates which are too large and are already in conflict with current experimental bounds. This is the case if the mixing angles are very large. And usually one would exclude this point from the phenomenological analysis. But if we now tune the phases, we can be in a situation where we can reconcile experimental data with our theoretical predictions. I want to conclude here that data needs to be interpreted very carefully in models featuring heavy neutral leptons, and CP violating phases always need to be taken into account, because it can mean that sizable mixing angles are still possible if phases lead to a suppression, but it can also be that we don't observe a certain observable which we should observe, and then again there can be a suppression of phases, and it should not mean that we should disfavor heavy neutral lepton models. So CP violating phases always should be consistently included in phenomenological analysis of heavy neutral leptons. So my take-home message is that, like in the quark sector with the CKA matrix, also in the lepton sector, you cannot spell flavor without CP violation. Thank you for listening and watching, and I'm looking forward for your questions.